Okay, very well. Good morning, everyone, and welcome to the Center for Theoretical and Computational Physics weekly seminar. Today, it is a pleasure to welcome Minghan Hu from ETH Zurich in Switzerland. Minghan did his first degree and his master's at Beijing University of Chemical Technology in China. This was followed by a PhD at the Max Planck Institute for Polymer Research in Mainz, Germany. And for the past 3 years, he's been a postdoc in the group of Lucio Issa at ETH Zurich. Today, he's kindly agreed to tell us about his work on self-assembly of colloidal nanomaterials towards multifunctional supraparticles. Now, before I hand over to Minghan for the truly interesting stuff, just a couple of announcements from me. First, this seminar is being recorded, so by staying on, you're giving consent to your voice and image being recorded and stored. Second, in the interests of internet stability, can I ask everyone to mute the microphones and turn off their cameras during the seminar, except the speaker, of course. If you wish to ask a question at any point, you are, of course, free to unmute yourself and turn on your camera if you so desire. Now, without further ado, it's on to Minghan for the seminar.
Yeah, thank you. Thank you for Paulo's nice introduction and also the very nice invitation. And it's my pleasure to present my work about the self-assembly of colloidal particles in this seminar. So today I'm talking about the self-assembly of the colloidal nanomaterials. Then we make it to the multifunctional supraparticles. And I will mainly talk about two main projects. One is I use the magnetic nanoparticles to assemble them together to make the anisotropic shape of the particles. And the other is I use the nanocapsules as the building blocks. Then I made the multi-compartments supraparticle. Yeah, then, but first of all, I would like to give my sincere thanks from all my the supervisor, my host, also all the collaborators regarding these projects. It's like the mainly thanks we give to Catalina and Hans-Jürgen and Luis, who supervised me. Also, we initiate these superparticle projects at the end of my PhD. Then I also continue this work in my postdoc place in ETH with Lucio. And we also develop this technique a little bit together with Andrew and also the professor in Xiamen University. And we can improve our technique and make the new structures of the supraparticles. And first, when we're talking about the particle assembly, and we know the assembly, it's like very like the childhood gameplay. We can, like the Lego bricks, we can just use our hand to connect everything, a building block together. Then we can make these assembled materials and microscopic size. But when we're talking about this micro scale or nanoscale assembly, obviously we cannot use our hand or our fingers to connect this nanomaterials. And because scientists develop a lot of techniques to assemble the nano building blocks to make these assembled materials. One of the most elegant or easy way to make the assembled particles is to use the Droplet Templates. So briefly, we can disperse our building blocks like the nanoparticles in the droplets. Then we can evaporate the solvents within the droplets. And during the evaporations, the nanoparticles inside the droplets will self-assembly and aggregate together to form the clusters of the particle, which we call supraparticles. And this technique is very useful and also easy to handle. For example, you can control the evaporation rates, and you can get the different surface structures of the superparticles from the random packing to a very crystallized packing with these specific crystal structures. Of course, because of the surface crystal structure are different, depending on these structures, we can have the different light reflections, and we will have the different structure colors, which is a very interesting applications. And also, we can use the different building blocks. For example, we can use these lignin-based particles. Then we assemble them together, and they can be used to do the carbon dioxide captures. Also, we can use it to make some catalytic reactions with them. And apart from making the spherical shapes of the superparticles, we can also people can also show them make these anisotropic shapes by controlling the nanoparticles interaction within the droplets. For example, you can add some salts inside the droplets. Because of the salts, then the particles, they will aggregate a little bit during the assembling, during the evaporation. Then they form these interesting anisotropic shapes. And of course, you also can control the contact angle and also the contact lights during the evaporation of the droplets. Then you can get the different shapes of the superparticles. And also, when you change the substrates where you evaporate your droplets, you also can get this like this very funny pancake or the spherical structure of the superparticles. But apart from that, we are thinking about we want to use a way that can control the shape of the particles by controlling the droplet shapes. And we got the inspiration from the this magnetic ferrofluids droplets. So we know if we apply the magnetic fields to the ferrofluids, which is the magnetic nanoparticles suspension, and they will form this interesting Rosen-Weiss patterns. And if we put these ferrofluid droplets on the superhydrophobic surface, and during this we increase the magnetic fields, we can see these ferrofluid droplets will split into these core-like micro droplets will split during the increasing this magnetic field. Once we decrease or remove the magnetic fields, these micro droplets can go back to the spherical shapes again. But of course, this shape is the transient shape. Once we remove the magnetic field, they cannot maintain anymore. And that's why then we are thinking about we can combine the technique we developed in our lab. This is the evaporation guided assembly ways. Simply says we have this super hydrophobic surface substrates. Then we put the droplets together with containing the magnetic nanoparticles. Then we evaporate the water, and during the evaporation, we apply the magnetic field. With this, we will expect that we have the end. Then with this, we first synthesize our magnetic nanoparticles. They are the iron oxide nanoparticles embedded in the polystyrene, and the size is around 100 nanometers. And with this, we first just drop our this suspension on the superhydrophobic surface. then just let it dry. Then we see what happens. So during the evaporation, because of the water evaporation, the droplet size becomes smaller and smaller. And at certain point, the buckling happens. Then after all the water evaporates, we get the final shapes like this buckling, like deflected ball-like structure. This is the top view of the microscopic images. And why this is happen? It's well explained in the literature. It's because during this evaporation, the particles, they tend to go to the droplet interface to form a shell. And this temporary shell, when it becomes thicker and thicker, it will maintain these shapes. And at certain points, it will just the buckling just happens because of the this force. And after all the water evaporates, then we got this deflected ball-like structure. And this is where it's already reported from the literature, and also nothing new. But what we are interested in is when we apply the magnetic fields in during the evaporation. And what we see here is the evaporation video, and we see also in the beginning change the size of the shape of the droplets, and at certain points it become it found these conical shapes. Then in the end we got this like conical structure of the superparticles, which is really interesting. And also we monitor this acceleration of the shapes during the evaporation. Then we compare it with the droplets without the magnetic field, then which we can see after 30 minutes we got these conical shapes, and in the end it maintained the shape. Then after the evaporation completes. Then why this happens? And so we go to this literature, and we know that for these ferrofluid droplets, when you apply the magnetic fields with the certain directions, then it will drag, or it can overcome the gravity, also the this capillary force. Then it can form these conical shapes. And of course, this height of the conical shape, it depends on these parameters. And we know that in our experiments we can control. It's not completely similar to this one because it's only the static state. And during our experiments, because of the water evaporation, the concentration of the droplets and also the surface tension of the droplets, they change. And that's why we during the magnetization of the droplet, we also change. But all of them we can still get an indication from these equations. And that's why we in our experiment we changed our magnetic particles concentration and also the magnetic strength we applied then to further investigate our particles formation mechanism. First, we apply the low magnetic field with the different concentration of the particles. As we can see here, at the beginning, we have these conical shapes of the particles, superparticles. When we increase the concentration of the nanoparticles, we got this barrel-like structure, like buckling things. And this from the video, we also can see this happens during the evaporation. So in the first stage, the cone structure growing, then we have this conical shape. But at the certain points, because this conical shape cannot overcome the shear formation force, and then the buckling happens. That's because we think this because of the magnetic field is not that strong. That's why we're seeing, okay, then we increase the magnetic field to see if we can overcome these buckling effects. Then we use the very high magnetic strength. Then we can see here yes, we can, we don't have this buckling structure anymore. Instead, we have this two-tower structure, which is similar to the video I showed you at the beginning. Then we have this, when we increase the magnetic field, then this splitting effect happens. Then we have these two-tower structures. This also can be confirmed during the videos here. Yeah. And with this, we can change the magnetic strength and also the concentration of the ferrofluids. Then we can draw this structure map of the superparticles. And the good thing is, based on this, we can also tune the magnetic directions of the during the evaporation, so we can form this like tilted towers after the evaporation of our magnetic droplets. And apart from using the superparamagnetic nanoparticles, we also use the different types of the magnetic particle, which is the ferromagnetic nanoparticles. And they also, we show them, we also can form these conical shapes, which is then is very good. And the good thing is we can also combine, use our this technique as the templates to combine different type of nanoparticles or different type of nano building blocks. For example, here we combine the titanium dioxides, which is the very useful catalytic, photocatalytic nanoparticles. When we mix these two building blocks together, we see that after the certain ratio of the magnetic nanoparticles, we can have these conical shapes, which means we can have these anisotropic shapes. And also we combine like the polystyrene, we also can see, we can clearly see this this brownish part is the magnetic particle and the whitish part is the polystyrene. They have the phase separation, but we can still form this conical structure. And the good thing is we can use the magnetic field to control the movements of our particles. And then once it reach the targeted place, we can, for example, shine the lights then to do the photocatalysis reactions and the specific place, which is really good. And therefore, we want to also check our superparticles magnetic properties after the assembly. And we see that our building blocks magnetic nanoparticles, they are superparamagnetic, which means then if we don't apply the magnetic field, there is the zero magnetic moment for our particles. Once we apply the magnetic field, it can feel the magnetic moments immediately, then move response to it. And compare with our assembled superparticles, it shows the similar magnetic properties, which is very good. Then we can guide our superparticles by the magnetic fields. For example, here I show, I just use the magnet to guide the motions of our superparticles. Then we can write the letters on it. Of course, we can do even more on it. And so this is the first part of the project. So in summary, we use the solvent evaporation guided self-assembly technique. We combine this with the magnetic fields. By applying the magnetic field, we can control the shapes of the droplets to generate the different shape of the different anisotropic shape of the supraparticles, which is very good, and we can in the future use them to do some application like the drug delivery, or also like to make some micro robots in these research fields. And of course, afterwards, and we thinking about our supraparticles, and usually the supraparticles, the building blocks, they are nanoparticles, which means they are solid particles. After the assembly, the structure, what we get here, as we can see, even we cut it inside, they have a lot of these particles connected together, but they are still solid structures. And but compared with these assembly techniques, our body is much more smarter. Like this is the one example in our lung, and we can see these small aggregates here called alveoli. It has these multi-compartmental structures, and they have these spherical shapes, and they assemble them together to form these aggregates. And inside they have the hollow structure, so they can contain the liquid and even the gas inside. This is also the way how we breathe every day. Like we have this inside, we have the oxygen, the oxygen. No, the carbon dioxide, this oxygen, then they can diffuse out to the capillary, and also like the carbon dioxide and oxygen, they can exchange through this multi-compartmental structure. So our next step, we want to make we want to mimic this structure to make the multi-compartmental structure to our supraparticles. And how to make this? Since the first idea came to our mind is we can use the nanocapsules, because the nanocapsule also has this similar hollow structure. They have this core shell structure, and this is the polymer shell, and inside we have the liquid core. With that we can encapsulate many different things like dye, drug, or even the message RNA, which is can be used for many applications like self-healing materials or drug delivery, or even the vaccination. With this, we think then we first synthesize these nanocapsules with this core shell structure, and then we use the same similar technique to assemble this nanocapsule together to form these aggregates. And with this, we don't have the we won't have this solid structure. Instead, we have the compartmental structure inside. And with this, we want to study if they can combine the different multiple functions from the single nanocapsule, or also with this multi-compartmental structure, maybe we'll have the new properties emerge. So in our experiments, we have these nanocapsules, and from the cryo TM, we can see these core shell structures, and this polymer shell is around 3 nanometer, and the total nanocapsule size is around, the diameter is around 200 to 300 nanometers. And then we disperse our nanocapsules in the cyclohexane droplets. To make these cyclohexane droplets, we use the microfluidics to generate this monodispersed size of the cyclohexane droplets in water, which is useful, which is very useful for our future study, because we have the similar size of the particles, and it's easy to understand or study their properties. And after evaporation of these cyclohexanes in the droplets, then of course the nanocapsule, they will self-assemble together in the end to form this super structure, which we call super capsules. And if we cut these super capsules, we can see the inside structure, and we have this very small nanocapsules containers here. And with this, we successfully fabricate this multi-compartmental structure. And the good thing is, with this technique, we can easily control the final supercapsule size by control the droplet size and the concentration of the droplets. Therefore, we show here, when we change these two parameters, we can fabricate our supercapsules from 2 micrometers to up to around 20 micrometers. And those are the microscopic images of our supercapsule with the different parameters fabricated. And with this, we also want to check if they can maintain or preserve the cargos inside the single nanocapsules. Therefore, we first encapsulate the different fluorescent dye, which is Psi3 and Psi5, inside the nanocapsules. And then we mix these 3 different nanocapsules together to form the supercapsules. Then we check the fluorescent microscopy. Then we clearly see they have this fluorescent color like yellow, red, together within the one single supercapsules, which means we can merge them to merge the different. We can combine the different building blocks together, and they still can maintain their functions inside. And furthermore, we encapsulate the magnetic nanoparticles inside our nanocapsules. Then we assemble this magnetic nanocapsule together to make this supercapsule. Then after the assembly, we can see that they can still maintain the magnetic properties, which we can also use this to guide our supercapsules motions. And this ties like a little bit one step further than the previous magnetic particles project, because with this we have the nanocapsules, which means it can carry the cargos, for example, the drug inside the nanocapsules together with the magnetic particles. Then we can really transfer our supercapsules to the specific place, then to release the drug or release the cargos, which is promising to for the drug delivery applications. And of course, because we have these multi-compartmental structures, and we are thinking about the release profile of our supercapsules, they should be different compared with the nanocapsules. Because as we know, for the single nanocapsules, if we have the cargo inside, for example, the dye, then the dye molecule, they will diffuse out to the environment because of the this osmotic pressures. This release profile or the release dynamics depends on the shell thickness and also the pore size of the shell, which we can tune a little bit to change the release time. But when we have these multi-compartmental structures, then you can imagine if we have the dye inside the center, once it wants to diffuse out to the environment, they have to pass through the shell of the this built nanocapsules. So we assume or we expect the release profile or release dynamics of the supercapsules will be different compared with the nanocapsules. That's why we did a study on this. First, for the nanocapsule is the very common one. Then we can see after around 4 hours, all the dyes can be released out to reach the equivalent. And we compare with the small supercapsules, and we can see the time, the complete release time increased to the 6 hour. Interestingly, when we increase the size of our supercapsules, the release time can be prolonged to 10 hours or even 16 hours, compared with the previous single nanocapsules, only 4 hours. And with we also plot this. So with this, we can know that we can easily or simply change the size, control the size of the supercapsules. Then the release profile can be completely changed. With this, we can compare with the current methods to control the release profile. And we use a very simple physical way to achieve it. And the more interesting thing is we can also control the inner structure of our supercapsules. And with this fully packed or closed package structure, and we can also make this hollow structure of the supercapsules, which we convert here from the SEM. And we found that if they have this hollow structure, the release profile of the supercapsules is similar to the single nanocapsules, which means because I think it's because of the this nanocapsule, the dye in the nanocapsule, they are close to the shell, then they can easily release to the environment. So with this, we can control the inner structure of the supercapsules, so then we can control the final release profile. And we also did do one thing more. Then we found that because our supercapsules, they are assembled together by the van der Waals force. So we are thinking about then we can apply the stronger force, like the sonication force. Then this supercapsule, they can disassemble again back to the single nanocapsule level. This is also what we did. We applied the sonication field to our supercapsules suspension, and only after 1 minute we can see our supercapsules from the around 10 micrometers then down to 1 micrometers, which means they've become these small clusters. And if we further increase the sonication time, the supercapsules can be completely disassembled to these single nanocapsule levels, which are around 200 to 300 nanometer size. Then with this also, we found that we can use this sonication to control the release profile of our supercapsules, because at the beginning we have the aggregates, this big supercapsule structure, and the release profile is follow the previous curve I showed. And then once we apply the sonication field, because the supercapsule, they disassemble to the single nanocapsule levels, and also then the release profile can be suddenly increased. So we can have this sustainable release change to the burst release on demand, just by applying the sonication fields. So with this project, then we can summarize that with this. We assemble the nanocapsule together to form this multi-compartmental structure of the supercapsules. With this, it can it can carry multiple cargos to realize the multiple functions, and also we can tune we can have the programmable release profile, and also the on-demand disassembly structures properties. Yeah, and so that's also all of my talks. So in the end, I would like to use this Richard Feynman's very famous sentence says, there is still plenty of rooms and buttons. So there is still plenty of room and the buttons of our self-assemblies. So we can still change a lot of, we can change the building blocks to make the different anisotropic structure. And also we can change the building block to have the different inner structure of our assembled particles. With this, we can imagine if we change the building blocks, we can easily extend the libraries of the supraparticles, and which can be used for different applications. And we expect in the future we have more and more interesting structure of these supraparticles can be paired and can be fabricated with these techniques. Okay, so that's all for my talk today. It's a little bit fast, and I would like to take questions from now. Yeah, thank you.
Okay, thanks very much, Minghan, for a truly fascinating talk. This is now open for discussion, so if you wish to ask a question, make a comment, etc., just raise the little yellow hand, and we have a question from Zemaria. Yeah, go for it.
Well, it was just a clapping sign, but yeah, but I also have a question, in fact. So I didn't understand, maybe you explained and I didn't get it. When you produce those cone-shaped drops, so they change shape when you switch the field off. They come back to spherical shape. I mean, you produce.
Yes, you mean this one here?
Yeah. If you so you produce those drops, evaporating the solvent with an applied magnetic field. That's how you produce the cone shape.
Yes, like this one we did. So we have the droplets, which contain the superparamagnetic nanoparticles.
Yes.
And then we apply the magnetic field.
Yeah.
Yeah. Then during the evaporation of the water, and the concentration of the these droplets increases more and more.
Yeah, I understood that. So my question is only, so what happens if now you switch off the field? Does it go back to a spherical shape?
So when we in this moment, if we switch off the magnetic field, because it's completely evaporated, so they only have the solid particles. So these shapes can be maintained forever.
Maintained. Okay. Yeah, so when you turn off the field, the shape remains. Yeah, the shape remains.
Because they are solid, and even you apply the different direction of the magnetic field, it doesn't change the shape. It just oriented together with the magnetic directions.
Okay.
Yeah, which we also use this property to show that we can guide this the motion of the particles. Like here, I show here, and also we write a letter with we just use the magnetic field to
okay.
Yeah.
Okay. Thank you.
Yeah. Thank you.
Right. Thank you. We have a question from Margarita now.
Okay. Thank you. I had a question. Maybe I didn't understand. When you talked about the release profiles, I suppose you're talking about the shells, and what is being released, and does it matter?
Yeah. So here what we release, here is only the dye we use as the model system. So
what?
we encapsulate the dye, the fluorescent dye inside.
It's a liquid dye, or what is it?
It's the liquid dye. It's the molecular weight is around 300,000.
Okay, so it's a liquid dye, and I mean,
the size is smaller than the polymer shell pore size, so it can diffuse out.
Okay. Yeah. So of course it depends what you want to release. I mean.
Yes. Yes, exactly. So now we show here is we only use the concentration difference to release the drugs or the model dye here. Also, then apart from this size in the literature, then people also use like they encapsulate the big molecular dye, which cannot be diffused out by itself. And then once they use the biodegradable polymer shell, once the polymer shell is biodegradable, and then the dye can be released. This is also another strategy. But here we only use the diffusion strategy to make it.
So the dye can diffuse without any rearrangement of the shell?
No, it's so it's only depends on the shell thickness. Of course, it matters because it takes time to pass through the shell. Right. Once so for example, this is the shell, and then the dye is passed through, and then the passing length it matters. And of course, the concentrations between inside the shell or outside the shell, it also matters because it's the pure fiction diffusion.
But I think I misunderstood. I thought you said they went through because they were smaller than the pores in the shell. But when I look at this picture they're showing now, it looks like the dye is replacing some of the shell particles. So is there rearrangement of the shell, or they just go through the pores?
They go through the pores. They go through the pores, then go outside to the environment.
But this figure is a little bit misleading, I think. No?
Okay. So what I want to say here is like the dye is just a schematic picture. Yeah, I can.
On the right.
Yeah.
They go through the pores. The answer is they go.
Yeah, they go through the pores and then can be released outside. Yeah.
Thank you. Thank you.
Yeah.
It's clear now. Thank you.
Okay. Very good. Any more questions? Who has a question? Well, I have a question. Your ferrofluid droplets, well, they're basically iron oxide particles in a polystyrene matrix. Is this right? Once the solvent has evaporated.
Yes. So the nanoparticle I use here is it has this hybrid structure.
Okay.
So as you can see these TEN images. So those are the black. If you see clearly, so this small black dot is the iron oxide nanoparticles, which are composites or encapsulates within the polystyrene particles.
Yeah.
So, and then we use this. So the total size of this iron oxide polystyrene hybrid particles, they are around 100 nanometers. And then we disperse these nanoparticles inside the water droplets. Then we apply the magnetic field, and during the evaporation, they form these different shapes.
Okay, and the final shape that you get, you said it's a solid, right? That's what you said a moment ago.
Yes.
Okay,
exactly.
but it's a rather soft solid, I would imagine.
Yes, it's you can say that it's soft solid. But so they cannot have these actuation things, but they can follow the magnetic field to move or to change the direction.
Okay. Yeah. Okay. What I wanted to know is, have you done any rheological characterization of these material, of this soft solid? Have you done any rheological measurements or on it at all?
Yeah, that's a good point. Yeah, but to answer this, we haven't done this rheology experiments on it.
And also, yeah, please go on.
Yeah, but I think there will be yeah, with this rheology experiment, then we can know the get more information on our superparticles, right? The mechanical properties, also like these things.
Okay, thank you. Any other questions?
Thank you.
Any other questions? If there are no other questions, can I ask another one? You did all these experiments on the same type of substrate, is this right? With superamphiphobia, you called it.
Yes. So these experiments, these ferrofluids experiments, what we use is the we call it superamphiphobia surface, which are synthesized in so in Max Planck in the Hans-Jürgen Butz group. So basically, they are the on the glass slide, and you coat it with the this wax stuff, and then it has this and then it do the further processing to make this like a pillar-like structure, which can be repel the liquids or maintain the liquids. So then even you put the water droplets or oil droplets, they don't spread on the surface. Instead, they maintain this spherical shape.
Okay, very good. But concerning shapes, I have one more question. You mentioned that when you apply magnetic fields to your droplets, they adopt different shapes depending on the magnetic nanoparticle concentrations. Is this right? For low concentrations, you get more cone-like structures, and then the barrels for high concentrations.
Yes, exactly. So for the low concentration of the nanoparticles, then during the evaporation of the water, then they form this core-like structure. And certain points, because they want to keep these conical shapes during the evaporation. But the particle, they form the shell and the interface. And this shell force, they tend to buckle. And then it's the competition between the buckling force and the magnetic force. So with the low magnetic field, magnetic strength, the magnetic force cannot overcome this, so buckling happens. That's why we increase the magnetic field in this case. Then we can see all the these superparticles that can have these conical shapes.
Okay, so what you're saying is a competition between the effect of the external field and the mechanical effect due to basically packing of particles at the surface.
Yes.
Okay.
Yes, absolutely. Yeah.
Right. Very good. Thank you. Any more questions, comments, criticism, praise, suggestions? Anyone? Well, apparently not. So I think we'll wrap up. Let's thank our speaker again for a truly fascinating seminar. Okay, Minghan, thank you very much for telling us about your work. And well, we hope to see you some other time at some conference, hopefully, hopefully in person. And yeah, do keep up the good work.
Yeah, thank you very much.
Recording stops now. Let me find this. Where's the recording button? Yeah.